In this video, which is also a continuation of chapter 7.8, we're going to look at the p family of curves where f of x is a function 1 over x to the p. So the question becomes, for what values of p does the integral, so what values of p does the improper integral from 1 to infinity of f of x, where f of x is a p family curve. So what values of p does that integral converge? And again, this is something that I'd like to prove for you in a minute, so that this will actually lay the framework for chapter 8. So there are 3 cases that we're going to look at. And I'm going to tell you when it converges, but I want to prove it to you as well. So when p is greater than 1, the p family curves, if I take the infinite integral from 1 to infinity of the p family with p greater than 1, this is going to converge specifically to 1 over p minus 1. If p is less than 1, then that infinite integral is going to diverge. And if p equals 1, it diverges as well. So I'm giving you that theorem, if you will, but I'm going to prove it in a minute. And we already saw an example of our first p family when we introduced improper integrals. I gave you the integral 1 to infinity of 1 over x squared dx. And here, p is equal to 2. And I told you that that integral evaluated to 1. So the area under that curve was 1. Well, using what we know now about the p family, it should converge to 1 over p minus 1 by the theorem that I'm going to prove. So it converges to 1 over p minus 1. Well, p is simply 2, so this is 1 over 2 minus 1, which equals 1. So that was our first little intro to the p family. So let's take a look at the proof. Here's just a visual of all the p family functions, and you can see what happens with it. It's an interesting case, and it's important to the study of infinite series. I'm going to pause here for a minute. So with the p family, sorry for the interruption, this is going to be important to the study of infinite series, which is what we're going to be covering in chapter 8 and 9. And what's important here is that this shows that a function must do more than decrease to 0 for its integral to converge. So if you look at any p series, as x gets bigger and bigger and bigger, this overall thing is going to go to 0, the limit. But it's more than just the limit of the function decreasing to 0 for its integral to converge. It must decrease sufficiently fast to 0. So with 1 over xp, this shows a function, the function must do more than decrease to 0. If I were to take the limit as x goes to infinity here, the function must do more than decrease to 0 for its integral to converge. And I'll show you this in a minute. Just want you to have this in your notes. The function must do more than decrease to 0 for its integral to converge. Okay? It must decrease sufficiently fast to 0. So it must decrease sufficiently fast to 0. Okay, so let's take a look at the proof, which will help us in Chapter 8. We're laying the groundwork here. Okay, so the proof for the three cases for the family of curves 1 over x to the p. So the integral, the improper integral that we're looking at is 1 to infinity 1 over x to the p dx. So as with any improper integral with an infinite integration limit, I'm going to rewrite it as the limit as b approaches infinity from 1 to b 1 over x to the p dx. And this is the same thing. I'm just going to rewrite this with a negative exponent as the integral of 1 to b x to the minus p dx. So let's take the antiderivative or solve the integral. So this is equal to the limit as b goes to infinity of 1 over negative p plus 1. All I did was take the antiderivative, right? So I add 1 to it and I divide by that exponent. So this is x to the minus p plus 1. Okay, so all we did was take the antiderivative here to get to here. This is the anti-d. Okay, so now I'm going to look at I'm just going to rewrite this a little bit. And I'm going to evaluate the limit of 1 over 1 minus p, x raised to the 1 minus p, and evaluate that between 1 and b. So this is equal to, so remember that the term 1 over 1 minus p is simply a constant. So this is equal to 1 minus p. I'm going to pull it out in front, and then I'm going to put in b and 1 into the fundamental theorem of calculus, and this is b to the 1 minus p minus 1 to the 1 minus p. And this term, 1 raised to anything, is going to be 1. So I'm going to rewrite this limit again. As 1 over 1 minus p times b to the 1 minus p minus 1. So I'm going to move this this exponent down and rewrite it a little bit. So I'm going to move that down, and this becomes the limit as b approaches infinity of 1 over 1 minus p times, to move that down, this becomes 1 over b to the p minus 1 minus 1. So to move this down, all that I did, let me grab another color, right, was if I move the negative p down, that becomes positive, and the 1 becomes negative. So this is just b raised to the p minus 1. So this is actually the limit. Now I'm going to look at the three cases. So now examine the three cases. And let's see what we have. Okay, so I'm working with this limit, and I want to look at p greater than 1. So if p is greater than 1, then the exponent in the denominator is greater than 0. So as b goes to infinity, 1 over b to the p minus 1 goes to 0, right? Because this is now positive, p minus 1, right? Because it's greater than 1, that's going to be positive. So this overall term as b goes to infinity is going to go to 0. So therefore, the limit as b goes to infinity of 1 over 1 minus p, 1 over b to the p minus 1, that goes to 0, as shown above. So the answer here is minus 1 over 1 minus p, which is the equivalent of 1 over p minus 1. So it converges to this, which is what I gave you a few minutes ago when I laid out the 3 cases. So that's the case where p is greater than 1. Well, what happens with p less than 1 and equal to 1? So if p is less than 1, then the exponent in the denominator is going to be less than 1, or less than 0. So, as b goes to infinity, 1 over b to p minus 1 is going to be a large negative, right? This is going to be a large negative number, or a large negative. It's going to flip up. Okay, it's going to cause the denominator, I'm sorry here. Since that is p minus 1 is less than 0, that's a negative exponent, so it's going to be a large number with a negative exponent. Let me rewrite that. So this is going to be a large number with a negative exponent, which is going to flip up. It's going to cause it to flip up. So this is going to become b to the p minus 1, which is equal to infinity. So the limit doesn't exist, which tells us that the integral diverges. So as p gets bigger, the graph seems to get closer to 0, but the term 1 over p minus 1 goes to 0. And b to the p minus 1 outgrows it. Okay, so that's your second case. Let's look at our third case. What happens if p is equal to 1? Then p minus 1 is equal to 0. So the integral 1 to infinity of 1 over x dx is equal to the limit, excuse me, I'm losing my voice here, the limit as b goes to infinity of ln of b, right? You have to replace this. Okay, and I jumped ahead a little bit here, but this becomes the limit as b goes to infinity. Taking the antiderivative of 1 over x, it's ln of b, and that limit as b goes to infinity is also going to go to infinity. So the limit does not exist. The integral diverges. So this is interesting. Again, this is important to note when the statement now hopefully makes somewhat of sense here. That the limit as x goes to infinity of 1 over x to the p. If I look at that as x gets bigger and bigger, and I look at solving that limit, we know that limit is going to go to 0. Why is this not working? That limit is going to go to 0. However, the limit going to 0 does not determine necessarily what's going to happen to the integral. Okay, so it has to do more than just decrease to 0 for the integral to converge. It's got to do that sufficiently fast enough. And what I showed in this proof is that here, if p is greater than 1, then it does decrease sufficiently fast to 0. And specifically, it's going to converge to this value, 1 over p minus 1. If p is less than 1 or p equals 1, the limit does not exist. Okay, and therefore the integral diverges of this term. So this is the p series is a very common series, and we're going to be spending a lot of time with this. So this was time well spent.